This lesson is completely dedicated to pin to animation. We will do it in a different way, covering all types of pinning. So, let's get started. Now I'll quickly introduce the scene we'll be using, and then we'll talk about pinning. Look, at the beginning I created this curve, then use planar patch from curves to build a plane based on it. This node is very similar to the planar patch node, it just creates planes from the input curves. Make sure you set the appropriate build plane. See, like a planar patch, you can control the triangle size. Okay, the next thing I did is created a simple animation, the geometry rotates around the specified pivot. Then comes the basic vellum setup. All vellum settings by default. Well, let's run the simulation and see how it looks right now. Nothing interesting so far, it just falls. Good, now it's time to talk about pin to animation. This small section dedicated to pinning points is also built into few constraints. Now I'll show you them. You see, on properties of hair constraint, there is the same pin to animation section. The only difference is that there is only one additional option related to orientation, which we will study when we get to it. The last constraint where it is also implemented is the string constraint, which is a lighter version of the hair constraint. We will also talk about it in the future. The pin to animation section built into the properties of these three constraints for quick pinning, but besides this, there is a separate constraint that includes all of this, plus gives you additional options. It is a pin to target constraint. See, you can pin both the position and orientation, as well as control the soft pin as you like. Okay, we'll use it soon. Now let's set back the cloth type of constraint and then check all pin types. See, there are three of them. I will start with permanent type. Let's pin some points and see what's going on inside the attribute spreadsheet. Select this piece and hit enter. Let's also turn on a pin to target visualization. Okay, now let's open the attribute spreadsheet and see what's going on under the hood. Look at the mass attribute. As you can see, some points have zero mass, and these are pin points. To make sure of this, let's visualize the mass attribute. Control-click on mass, and Houdini will automatically set a visualizer for this attribute. You see? The pinned area turned blue, that is there the mass is 0. The permanent type of pin makes the points a hard constraint, zeroing the specified point's mass. It turns out that we can ourselves zero the mass where we want to pin points. Now let's remove the point numbers that we pinned and then drop down the attribute paint node to draw zero mass. Since mass is a point attribute, we connect to the geometry stream. Let's enter the name that we are going to draw, then set 0 and start drawing. Well, now let's check the result. Look, where we drew the 0 value, the pin to target visualization spheres also has appeared. Let's check whether they are pinned or not. That's it. We were able to pin them by zeroing out the mass. I'll paint somewhere else and check again. Turn on the mass visualizer, then run the simulation. There you go. Everything is expected. Okay, with zero mass, everything is clear, let's move on. The next thing I want to talk about is the match animation option. Let's see what's going on under the hood when we turn it on. But before we check this option, let's pin some points. So now let's open up the geometry spreadsheet and see what happens when we turn it on. See, a new point attribute was created. Let's hide them all and show just this. It is glue to animation attribute. Look, it disappears when we uncheck the match animation and appears when we check it back. If glue to animation is 1, the pinned point's position and orientation will match the target animation, and 0 will not. So now let's check the result. As you can see, the pinned points already follow the animation. Now let's make it so that at some point, unpin it and let it fall freely. For this we only need to change the value of glue to animation from 1 to 0 inside the dot network, and this can be done with geometry wrangle. Unlike the vellum constraint properties node, the geometry wrangle will touch the particle attributes. If you check the binding data, you will see that it refers to the geometry. Now let's create a vellum constraint property node and check its binding data. See, it already refers to the constraint geometry. Well, let's switch to the geometry spreadsheet and find both geometries that these nodes refer to. Look, here is the geometry object. It stores all the particle attributes, and geometry wrangle refers to it. That is, we can manipulate all these attributes with geometry wrangle. And this is already the constraint geometry object that contains all constraints attributes, and the vellum constraint property node refers to it. Okay, let's move on. We already can delete this node, we no longer need it, then back to geometry wrangle. Now I'm going to set a condition so that when it is true, the glue to animation attribute turns to 0. Let's type the following. If the current frame greater than 72, the glue to animation is 0. So now let's check the result. See, after frame 72, it stopped following the animation, but we couldn't unpin it, it just stuck in place, and this is because the mass is still 0. This is a limitation of the permanent mode. Since the original mass value is not stored, it isn't possible to release this constraint later. Now let's switch to the second type of pin, then open the geometry spreadsheet again and see what's going on there. Look, there is a new integer attribute, and it is called stopped. If we go back to the permanent type, it will go away. The stopped attribute is set to 1 to make the point a hard constraint. The mass is unaffected, so later we can reset the stopped attribute to 0 and restore the dynamics of the points. Well, let's do it now. Add a new line inside brackets, then type the following. The stopped attribute will be 0 when the condition is true. Okay, let's see what we get. There you go. It unhooked and started to fall. To make it more spectacular, I propose to slightly increase the speed of rotation so that it flew far away when it was unhooked. Looks nice. I think we can move on. If you like working with VOP, you can use geometry VOP instead of wrangle. You can even use the pop VOP node or just pop wrangle. Now let's copy the code, then paste it to the pop wrangle and check if it works. See, the result is absolutely the same. All the nodes provided for the particles will work on vellum points. Well, with this example we can already finish. I have another interesting example related to pinning and unpinning, so let's get to it. This time we'll use a pig's head. This is a basic vellum setup, all vellum properties by default. Let's play and see. Nothing interesting yet. Now I am going to fracture the pig's head into many pieces. For that we will use the edge fracture node, which cuts input geometry along existing edges. To see what happened, let's visualize the primitive pieces. Since the initial pieces are set to 10, the pig's head split into 10 pieces. Now let's decently increase the number of pieces. See, the size of each piece has become much smaller. To make sure the pieces are separated from each other, let's drop down the exploded view and check. That's it, they are all torn apart. Okay, we can move forward. Now let's run the simulation and see how it looks. See, all the pieces fly in different directions, which is quite expected. So now I want to do the following. At the beginning, freeze them all, and then activate them from top to bottom during simulation. So let's dive into DOP and create a geometry wrangle. Connect to the force output, then type the following. Integer at stopped equals to 1. That is for now, we just stopped them. Look, they're not moving anymore. Now we will activate them in the direction from top to bottom. For this I am going to use the group node. Connect fractured pig's head to it, then adjust the group node parameters. Specify the points and call it a trigger. Then turn off the base group and enable the keep in bonding regions. Increase the bounding box size, then move it up so that all the points get inside it. Okay, now let's turn off the simulation and then start animating the position of the bounding box. Look, as the box goes down, the points gradually leave the group. So we will use this group to activate particles. Let's also create an output null to refer to the group later inside the dynamic network easily. I will call it outGroup. So now let's dive into DOP and use this group. First, we must refer to it. Let's set up the inputs. Select outGroup and press accept. See, we specified the geometry containing the group in the first input. Well, now let's import the group to Vex. Let's create an integer variable on a new line and call it trigger. Then, I will use the inPointGroup function, which returns 1 if the points are in the specified group. If not, then it returns 0. Now we will replace the stop value with this variable. That's it, let's check the result. As you can see, everything works fine. We just controlled the stopped attribute with the trigger group. Let's change the direction of gravity upward so that they rise up instead of falling. I also want to add some noise so that they do not rise evenly. Let's use the pop wind. Set a small amplitude. Then increase the swirl size. That's all, let's see what we got. Here we go, we got a nice result. Okay, now let's look at the case when the geometry is animated. Let's get out of the DOP network, then make a simple animation. Drop down the transform node. Then we are going to move it along the negative x-axis. So I will use the current frame expression to drive it, but multiply it by a small value to slow down the movement speed. Okay, I am happy with this, let's move forward. Now we need to pin all points to this animation and then unpin them by using the trigger group as we did it recently. To do this, we will use the already familiar glue to animation attribute, the values of which will also be derived by the trigger variable. Okay, let's check what we have now. As you can see, it doesn't follow the animation yet. Now I'll show you what the problem is. Let's go to the solver settings, then look at the advanced tab. See, this defines the target geometry to which the points marked as glue to animation will be attached. See, the default is set to the first input, but at the first input we have no animation. Now let's move the animation to the first input and see if it works. There you go, it started following the animation. In case the animation is in a different location, you can specify the path to it. Choose here SOP path, then select animated geometry. Okay, let's check again. As you can see, we got the same result. I think if we also add the pig's head as collision geometry, the result will be much more interesting. So, let's do it. Since the collision geometry should move with it, let's create a reference copy of the animated transform node to move the collision geometry separately. Connect the original pig head to it, which is not fractured. Then we'll narrow it down a bit to create a small gap between the cloth and the collision geometry. With peak node, we can move primitives along their normals in a negative direction and narrow it down. Well, the collision geometry is ready. We can feed into the collision input. That's all. Now let's arrange the nodes so that the setup looks neater. Press Shift S to change wire style. Okay, now let's see how it looks with the collision geometry. Obviously got a lot more interesting. Let's take another look. With this simple technique, you can make a cool peeling effect. Well, now I want to show you something else, and after which we will complete this lesson. See, instead of glue to animation, you can use the pin to animation attribute, which the solver also knows about. The difference is that the pin to animation attribute only pin positions, but the glue to animation pin both position and orientation. Since there is only a position in this case, there is no difference at all, so the result will be the same. Okay, that's all for this lesson. In the next lesson we're going to discover the soft pin type, as well as the pin to target constraint. See you in the next lesson.